In this video, we'll talk a little bit about quantum gates. So we'll talk about single qubit, two qubit, and three qubit gates. So according to the second postulate, the evolution of quantum system happens via a unitary evolution. So quantum gates are evolution of a quantum system, and this evolution is governed by a unitary operator. So gates are unitary operations, and particularly in qubits, they are on the unitary operators on the space C2. So let's take some examples of single qubit gates. So there are gates called the poly gates. So let's take a look at the poly gates. These are these X gates. So X gate is takes. So this is a gate that takes alpha 0 plus beta 1 to alpha 1 plus beta 0. So it flips the 0 to a 1 and 1 to a 0. So the matrix representation of this gate is an operator in C2. It is 0, 1, 1, 0. So as you can see, it will take the 1, 0 vector to 0, 1 and vice versa. So this is the quantum equivalent of the NOT gate. So this is called the quantum NOT gate. This is the quantum NOT gate. When similarly, there are other poly gates. There is and these are important gates. They are not only unitary operators, but they are also Hermitian operators, and they represent the observables that measure the qubit in the X, Y, and Z direction. But as I said, they are also unitary operators. Y gate is represented by this matrix 0 minus I 0. So this is the Y gate, and the Z gate is 1 0 0 minus 1. So it takes the Z gate takes alpha ket 0 plus beta ket 1 to alpha 0. So it doesn't change the basis vector 0, but it adds a relative phase to this state, and it takes ket 1 to minus 1. So a phase is added over here, a relative phase. Okay, so another important example of a single qubit gate is the Hadamard gate. So it changes. So the Hadamard gate will be later pretty important. So Hadamard gate is takes alpha ket 0 plus beta ket 1 to alpha ket plus beta ket minus, where plus is the superposition of 0 and 1, and minus is this 0 minus 1 over square root of 2. It turns out that plus minus, just like ket 0 and ket 1, are also a basis of C2. In fact, they are an orthonormal basis. And so the Hadamard gate converts this ket 0, ket 1 basis to ket plus, ket minus basis. So that's the Hadamard gate. Well, there are other gates as well. Like, for example, there are the S gate, which is called the phase gate, is 1 0 0 e to the I pi over 2. And then there is the T gate, which is equal to 100 e to the I pi over 4. So we get t square is equal to s. And notice that these are unitary matrix, so they can have complex entries. So the gates are represent the evolution, and a typical quantum circuit will have a wire, maybe an initial state ket 0. Then there will be various gates U1, U2, and so on applied, maybe UN. And finally, after some reasonable time evolution, there will be a measurement to get a classical answer. In the meanwhile, there'll be gates. Now I'm representing only single qubit gates, but there could be multi-qubit gates also. For example, in the 2 qubits. So let's go on to the 2 qubits. So an important example of gates in 2 qubits is the C0 gate. So gates on 2 qubits. So the C0 gate is a gate which again is the classical analogy is the classical C0 gate. So it is represented like this, and it takes this. So this will the top wire will be the control wire. So control, and then the bottom wire is the target. So it takes input, which is the tensor product of this control and target, and converts it to, so the control bit doesn't change, and then this is C plus T. So this is C tensor C plus. This is the XOR of that. So let's see what happens to the basis state. So if I the action of the C0 gate on these basis vectors will help us write the matrix representation of the C0 gate. So ket 0, ket 1. So this is C, this is T, and then this is 1, 0, and 1, 1. So this will be 0, 0. So if the control bit is set, then the target bit gets flipped. So this is, in this case, the control bit is not set. So this will be 1, 1, and this will be 1, 0. So this is C, and this is CO plus T. Right. So these are the action of the C0 gate. And if I, from here, I can write down the matrix representation of the C0 gate, which will be a 4 cross 4 matrix. So this will be 1, 0, 0, 0, because 0, 0 goes to 0, 1. Then 0, 1 also goes to 0, 1. So this will be, and then 1, 0 goes to 1, 1. So therefore, this will be, so I'm just writing down the column vectors which represent the action of the linear operator on that basis vector. So this will be 0, 0, 1, 0. So this is the matrix representation of the C0 gate. And as you will see later that the C0 gate is an entangling gate. It can, for instance, if you take the input to the C0 gate, which is, so if I take the C0 gate and give it this input, and uh, right, the control bit is 0 plus 1 over square root of 2, then the what will be the output over here? So this will be 0 plus 1 over square root of 2 tensor get 0, and the C0 gets applied, right? So one can use the linearity property of the C0 gate. So this will be same as applying C0 to 0. C0 gets applied to 0, 0, um, plus C0 gets applied to 1 tensor 0 over square root of 2. So this is equal to 0, 0, This won't change, and this will be 1, 1 over square root of 2. So this is, it starts with the product state of the control and target bits and ends up with an entangled state. So this is a entangled state. So C naught gate is an entangling gate, and it will be an important gate. Our entangling gates will be important because when you want to build a quantum circuit, you just don't want to have just product states being created, but you also want to use the power of quantum computation to use entangled states, and those entangled states are generated by entangling gates such as the C0 gate. All right, so let's move on to the 3-qubit gates. So 3-qubit gates. Well, I will give examples of two of them. One is okay. Another example before I do that. Another example of a of a 2-qubit gate is this swap gate. So let me just write this uh, swap gate. So swap gate is represented like this. So it just swaps the 2 qubits. So this is A, B will go to B, A, right? So 0, 0 goes to 0, 0, 0, 1 goes to 1, 0, and 1, 0 goes to 0, 1, and 1, 1 goes to itself. So the matrix representation is 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1. So that's the swap gate. And finally, we have a 3-qubit gate. So 3-qubit gates. So one is the Toffoli gate. So this is again comes from classical computing also. So the Toffoli gate has two control bits and one target bit. So if the control bits, both the control bits are set, then the target bit gets flipped. So this is control, this is C1, this is C2, and this is the target bit. So this will be C1, this will be C2, and the target bit gets flipped if both C1 and C2 are set. So this will be C1. So if both are set, then the target gets flipped. So this is the Toffoli gate. And then an exercise to show this matrix representation of the Toffoli gate will be an 8 cross 8 matrix. So this will be a, because this will be 2 times 2 times 2. The dimension of the Hilbert space will be 8. So this will be 8 cross 8 matrix, right? And then finally we have the Fredkin gate, which has one control qubit, and then if the control qubit is set, then the second and the third qubit gets swapped. So C and then A and B. So these qubits get swapped if control qubits C is equal to 1. Okay, so that's about quantum gates, but more than the gates, I think it's important to sort of understand the concept of universality of quantum computation. So in classical computation, we know that the NAND gates are universal for classical computation. I can write any classical circuit using NAND gates. So there is a similar theorem in the case of quantum, but in the case of quantum, what we want to do is have a discrete set of gates. Now, there are on n qubits, you can construct infinitely many unitaries, right? But what we want is a discrete set, and the reason is for error correction and fault tolerance. So we want a discrete set which can be universal for quantum computation. And so what we want is, instead of exactly um, um, coming up with a target unitary, we want an approximation to a unitary. So we want something like this. So there is a n qubit unitary U, which is acts on n qubits. And what we want, an important problem in quantum computation is to find sort of a set of gates, a discrete set of gates. Let me call them H, T, S, and C naught, that will approximate this n qubit unitary. So, which means that I can come as close as possible in some sense to this unitary using this discrete set of gates. So some circuit that looks like this. Right. So let me just define. And also the other thing is that we want to make this as efficient as possible, which means that ideally we want the number of gates that we use in over here to be some order of polynomial of n, where n is the number of input qubits, right? Because if they are exponential, then of course it's not a very efficient quantum circuit. So let's define universality in that sense. So universality, set of gates, definition, universal set, right? So a set of gates G is universal for quantum computation if any arbitrary unitary U can be approximated to any precision using gates only from the set G. So it turns out that the set G, consisting of H, S, T, and C naught gates. These are single qubit gates. These three are single qubit gates, and C naught is a 2-qubit gate, are universal. So one can take any unitary and construct it using these to an arbitrary precision. However, I must mention that an arbitrary unitary cannot be approximated efficiently by this set. In general, most unitaries will require an exponential number of gates. So the main one of the main focus of quantum computation is to find those unitaries or find algorithms which are efficient and can be constructed using a polynomial number of gates. And one such example is the Shor's factoring algorithm, which takes a set of gates which are only quadratic in the number of input qubits.